Hi there! In this session we're going to calculate singular values of a matrix and perform singular value decomposition of matrix. Singular values are related to eigenvalues. However, unlike eigenvalues, singular values are defined for all matrices. And you know that eigenvalues are only defined for square matrices. SVD is a decomposition of this form. You can express a matrix of any size as this product, a unitary matrix U times by a S matrix which contains singular values of this matrix as its diagonal elements, and finally V transpose. Both U and V are unitary matrices. That means U transpose equals to I, the identity matrix, and V transpose is also equal to I, but with appropriate size. And generally, if A is of the size m by n, then S is of the size m by n, so U is m by m and V is n by n. And S is generally in this form. It contains some values called sigma or singular values here up to some, for example, m or n, the minimum amount of this m or n. And if for cases that you have m greater than n, the matrix will be in this form, and for the cases that m is less than n, it's in this form, and for the equal case it will be square. And all of these elements are 0 whenever they exist and the S contains this row or this column or this set of rows or these set of columns. This will not exist in any case. Okay, these singular values, let's name these singular values, are in descending order. So sigma, the first, is larger than or equal to sigma 2 and so on. And finally, all of them are greater than or equal to 0. And all of them are non-negative. In fact, the singular values of a matrix are eigenvalues of this matrix, A transpose A or A transpose. And just because of that, we have A transpose A as a symmetric matrix and A transpose as a symmetric matrix, then we know that all eigenvalues of symmetric real matrices are greater than or equal to 0. So all of singular values of a matrix are non-negative. Okay, enough theory. Let's calculate singular values and singular value decomposition of a given matrix. Let's define a matrix, for example, of the size 1, 2, 3, 4, 5, and 6. It's not a square matrix, and so it has not eigenvalues, but you can calculate singular value decomposition for this matrix using this function SVDA. But this function has 3 outputs: U as its first output, S or sigma, and V. And you see that the same size as our original matrix, and these are our singular values, and the order is descending, and all of them are non-negative. And this is U and V, and you can calculate U times S times V transposed, and you get A, almost A. And if you calculate the difference, it's almost 0. So we have the singular values of this matrix, and you can calculate the diag of S, and these are singular values. And if you calculate the eigenvalues of A transpose, that's it. But you must calculate the square root of this, and that's 0.51 and 9.52, and that's it, 9.52 and 0.51. Just for some round of or numerical errors, we have a negative number here, very close to 0. And if you calculate A transpose times by A, you get the two singular values of this matrix. So we can correct this. Singular values of A are square roots of these eigenvalues. And we see that the equality holds here. However, we have U in this way, S and V, and this column of U is not needed at all, and this row of S is not needed too. And you can ignore this column and this row. For example, U, all rows but the first two columns, and S, the first two rows and all columns, times by V transpose, and you get the same matrix. And you can delete the unneeded elements when you call the SVD function by passing a economy or economic flag, and you get the economy size SVD of the matrix, and the equality holds for the matrix, and the unnecessary elements, rows and columns, are removed. But an interesting fact about SVD is its relation to the amount of information contained in the matrix, and it is somehow very closely related to a technique we know as principal component analysis, PCA. It's a technique of dimensionality reduction which is highly used in context of machine learning and artificial intelligence, and it is extended to nonlinear cases. But for now, let's see a little bit more about the informational concepts behind the SVD. Remember that we have U, S, and V in economy size, and I think the 9.5 is much more greater than this element, and let's remove this row and this column. And if you remove this row and this column, you'll remove the last column of U and the last row of V too. So let's calculate this function by removing the last column of U times by S, which contains only the first row and first column, times by V on removing the last column but transposed, and that means they're removing the last row. So we calculate this, and it is very close to our original matrix, 1.3, 1.7, almost close to 1, 2. For 3 and 4, we have 3 and 4 here almost, and it's 5, it's very close to 6, and it is very close to the first matrix, our original matrix, but it's not exactly. It contains some errors, which is due to deletion of this small singular value. If you removed this value, you'll get nothing at all, nothing meaningful. But keeping this singular value preserve a large amount of original data. Let's perform an interesting calculation on an image. You can do it on images, and it's a well-known technique to compress the images. Let's clear the workspace. Let's read the image, and let's read one of the images available in MATLAB. For example, cameraman.tiff. That's a well-known image. Let's suppress the output by putting a semicolon. If you show this, you'll see the image. However, if you open this and you see here that it's a unsigned int of 8 bits, and it's not good to perform real calculations on this integer type, and so let's convert this to double after reading, and that converts the image to double, and all the values are in the range of 0 to 1. And if you show this, you'll get the same image. But if you perform SVD on this image, SVD of this image, you get, suppress the output by putting the semicolon. S is a square matrix, U, V, all of them are square matrices, the same size as the original image. And if you get the diagonal elements of S, you see that the singular values of the image are listed in the descending order, and one of them is very big and it contains a large amount of information of image related to the image. And for example, you see that we have 256 singular values, and let's preserve just 10 of them. Or let's start with the first one. For example, image 1 goes to U all rows, and the first row, and S from the first row to the first row to the first column. I intentionally write this in this way, and V all rows and first column to the first column, and transposed. If you show this image somehow similar to our original image, let's define another image, for example 2U2. You see that we created another image, and if you show this image, it's clearer than the previous image, it's more similar to the original image. And let's define some function, for example Q, which returns U from the first column to the nth column, and it's the function of n, and times by S 1 to n, 1 to n, times by V 1 to n transposed. And it's a function. If you show the Q1, it's the image 1, and if you show the Q2, it's the second image, which contains 2 singular values of the original image. And if you add some other eigenvalues, here the cameraman is somehow visible, and for the 4 singular values, for the 5 singular values, and for example for the 10 singular values, you see that the cameraman appearing. And if you use 20 singular values, and you can for example use 50 singular values, and it's almost visible. But we used only 50 singular values out of 256 singular values. That means that we have used only 20%, 1 per 5 singular value of the original image. And you see that some noises are visible here, and these are due to the deletion of some components related to small singular values. So you see that singular values are related to the information, and they can be used to compress data, and also they can be used to lower the dimensionality of a given data in such a space way, and that's the well-known method of principal component analysis.